using an internal GAN. Yeah.
What's that? Hi, I'm Sefi, and this is Asaf, and we'll be presenting our joint work with Michal Irani, which we call Kernel Gun, and we'll show you how we can estimate the super resolution kernel for blind super resolution. But first, what is super resolution? It's a pretty straightforward definition. We have a low resolution input image, and we want to produce the high resolution version of it. This is the task, where every pixel in the low resolution is an average of the surrounding pixels in the high resolution. That is to say, it's a result of a convolution with the kernel K and subsampling. Now, this kernel will play a main role in our talk, and here are some examples for it. It varies in shapes and in sizes, and it depends not only on the camera taking the picture, but also on other effects, such as the shake of my hand when I took it. And therefore, it varies from image to image, and it is image-specific. And now, recovering the high resolution is highly ill-posed even if we have known the kernel, even if we have it. And it's not surprising that the leading super-resolution methods use deep learning. However, these methods implicitly assume a single ideal kernel, a single ideal low-pass filter, which is obviously when the world is not ideal, this assumption is wrong, and as we'll see, when they assume the wrong kernel, these methods perform poorly. This observation gives rise to blind super-resolution, where in blind super-resolution, nor the kernel, we don't have neither the kernel nor the image, making this task this much harder. In this work, we will show you how we can extract information directly from the low-resolution image. We'll show you how we can estimate the image-specific super-resolution kernel. We do it in a fully unsupervised way using 0 other examples. We train on the input image only, and we do that at test time. We also will introduce the first practical use of deep linear networks, and all these together allow us to introduce state-of-the-art results in blind super-resolution, but more importantly, it allows us to do real super-resolution without any prior assumptions, what we call super-resolution in the wild. But first, what is the problem with existing methods? The majority of them take a large data set of many pairs of low-resolution and high-resolution images, and they train exhaustively a network for days or even for weeks to learn this relation. And then they take the network and apply it to any image in the world to perform super-resolution. And typically, there are 3 types of these methods. The first type implicitly assume a single ideal kernel, a single ideal low-pass filter, such as the bicubic kernel. And since I'll shake my hand in a certain way in one picture and I'll shake it a different way in another picture, this assumption is wrong, and we'll see that they perform poorly when this assumption does not hold. The second type of method try to be agnostic to their kernel. They try to perform super-resolution regardless of the image-specific kernel, and they do it by training on multiple kernels. However, also here, when in real images where the kernel is not necessarily one of these set of kernels, they also perform very poorly. The third type of method expect to receive the kernel with the image. They expect someone provides them with the kernel at test time. This is where we step in. We'll be the ones providing these methods with the kernel. But first, let me convince you of the importance of it. Here's a low-resolution input image, downscaled with a non-ideal kernel. This is what happens when I just interpolate it. But if I take state-of-the-art super-resolution, this is what happens. And now if I flicker between the two, can you tell the difference? The answer is no. It's because there is no difference. State-of-the-art super-resolution cannot do any better than simple interpolation when their assumption does not hold, when it's not an ideal kernel. But if I take the correct kernel and just plug it into a simple super-resolution method, this is the result. And now when I flicker between the two, you can all tell the difference, just by using the correct kernel. And as you can see in this image, and it was shown explicitly in several papers, the correct super-resolution kernel is in fact much more important than the specific super-resolution method. And with this in mind, we ask ourselves, how can we estimate the kernel? What do we know about it? Remember, all we have is our input image. We don't know the high-resolution image, nor the kernel connecting the two. But this is the super-resolution kernel. This is the one we would like to estimate, and this is the one those methods expect to receive. But what do we know about it? It was shown in a paper by Michal and Irani that the correct super-resolution kernel, in fact, also maximizes the patch similarity across scales. What I mean by that is if I take the super-resolution kernel and downscale the image, I'll get patches from the input image and patches from the downscaled image as similar as possible, meaning the patch similarity will be maximized. And Mikhail and Irani also provide an analytical proof for this specific observation. You're also welcome to come to the poster for further explanation. But with this phenomena in mind, how can we estimate the kernel? Remember, all we have is our single low-resolution input image. What we do is we use our Kernel Gun. It's a kernel estimation method using an internal GAN. While standard GANs train on multiple images, learning those image distribution or the distribution of those images, an internal GAN trains on the single image. It learns its unique distribution of patches of that image. How do we do it? We take the input image and we pass it through a downscaling generator. Remember, we're looking for the specific downscaling that maximizes the similarity of patches. Now, how can we measure this similarity of patches? How can we guarantee this? So we use a discriminator, obviously. We take patches from the downscaled image and patches from the input image and pass them through the discriminator. This discriminator now tries to distinguish which patches are real from which patches are fake, namely which patches came from the distribution of patches of the input image and which patches came from the distribution of patches of the generated image. And if it cannot distinguish between the two, it means that the patch similarity is maximized. And if the patch similarity is maximized, G converged to the correct downscaling, the downscaling with the correct super-resolution kernel. And there we have a framework that can estimate the kernel when all we had is the input image.
So what kind of generator do we need here? A standard neural network is unlikely to model this linear downscaling. It will generate patches from the same distribution, perhaps something like this. Now the discriminator's happy, the generator's happy, but this is clearly not what we wanted. What we really want is for the generator to imitate this linear downscaling operation. Now convolution and downscaling, convolution and subsampling in deep learning terms simply means a single-strided convolutional layer. So indeed, we tried a single-layer generator, and we tested it over a large set of ground truth kernels. And this has to work, right? So unfortunately, we got terrible results. And it took us quite a while to figure out why it felt so bad. And we got to this conjecture. So the basic paradigm of deep learning says that there are no bad local minima. So whatever initialization you start from, you'll be able to converge to some reasonable set of parameters using gradient descent. In our case, there is only one good solution, which is the ground truth kernel. So this is the only set of parameters that is good for us. And you have to keep in mind that the loss for the generator is the discriminator, which is highly non-convex. So there is no chance for converging to this single minimum point from just some random initialization. So while this model is functionally correct, in practice, it is just impossible to optimize. If, however, we use a deep linear network, this solves the problem. How come? Well, a deep linear network is simply a network that has no ReLUs, no batch norms, none of this stuff. And I guess some of you may be thinking right now, wait a minute, this is stupid, right? Because if we just multiply all these layers together, then we'll see that this is exactly the same, just as a single layer. And this is sort of correct, because these are just factorizations of this single layer network. The thing is that there are infinitely many of these. So for example, you can always multiply one layer by A and the next layer by the inverse of A for any invertible matrix A, and you'll still get the exact same mapping. So this means that we're now getting infinitely many good minima. And now this thing can converge from any initialization. So we tested it again, and comparing to the awful results we had before, now we're getting good results that we're happy with. And it's also worth mentioning that deep linear networks were mainly used for theoretical research, but this is, as far as we know, this is their first practical use. OK, so let's check out some results. So here's an input image, and it was downscaled by an unknown kernel. And this is the result obtained by the state-of-the-art non-blind method. And this result is obtained by ZSSR when fed with the kernel provided by the kernel GAN. And if we flicker between those two, then you can clearly see that our result is much sharper. But let's see what happens when we compare two blind methods. So PDN was the winner of the blind super resolution entire challenge. And if we flicker again, you can see that it has some artifacts in the lip and in the nose over there. And you can also see that our result has much clearer details. For example, the fibers of the sleeve over there or the details of the eye. So what happens when we go to real-world super resolution? These are images that have no ground truth and the downscaling process is unknown, like this Kennedy image that we just took from the internet. And you can see that the blind methods either introduce severe artifacts or they do this really bad over-smoothing. So the kernel estimation methods do much better. And you can see that our kernel GAN actually produces the best results, both in terms of accurate details and both has less artifacts. Here's another example. So here you can see that even in the presence of some compression artifacts, the best result is obtained using a kernel that was provided by Kernel Gun. You can see many more of these results in our website. So as for the quantitative evaluation, so we tested against the non-blind methods that assume an ideal kernel, and also for the blind methods that try to be kernel agnostic, and finally also against the former kernel estimation method fed into two separate types of super resolution. Bottom line is we get much better results and we outperform by a very large margin. So to conclude, we introduced Kernel GAN, which is a kernel estimation method that uses an internal GAN, and it is totally unsupervised and requires no prior examples. The training time is about a minute on a GPU, and this is regardless of the image size since we train it on image crops. This is also the first practical use of deep linear networks, and most importantly, it brings to state-of-the-art results for blind super resolution, which is a step towards what we refer to as super resolution in the wild, which is super resolution without any prior assumptions. So thank you all for listening, and to learn more, please visit us at poster number 87.
So we have time for maybe one question at the mics.
We'll do a very blind reconstruction. In this case, do you violate the sampling theorem? There, you don't have any information at all.
Could you repeat, please?
Do you violate the Nyquist sampling theorem?
What about the Nyquist sampling?
Whether it is at all possible if you don't have any information.
Okay, so this whole set of super resolution methods is only possible because of some priors on natural images. In this case, the strong prior we take advantage of is the recurrence of patches or the recurrence of information and the fractal-like behavior of natural images.
But you don't have a reference, right? In your training, this is completely unsupervised.
No, we don't have any reference. We have only
so
the
original image can be anything.
Right.
And
right.
then what guarantees you to recover that?
So the thing that guarantees is the recurrence of information inside a single image, so that you have the reference is inside the image. One area of the image can provide some reference to another part of the image.
Even in the original training set, you don't know what's the original image at all, right? So even that information is not there.
There is no training set.
There's no training set?
Only one input image.
Just one single image?
One single image.
Okay, sure.
Yeah.
Now moving into a 5-minute each spotlight presentation. Thank the speaker.
Hi, my name is Kimia, and I'm going to present our theoretical study on estimators obtained by minimizing the slice-Wasserstein distance. The problem considered here is called minimum distance estimation, and it consists in minimizing a distance between mu hat n, which is the empirical distribution of our observations, and mu theta, which comes from a family of parametric distribution. This is a generalization of maximum likelihood estimation, which corresponds to the special case of D being the KL divergence, and several statistical problems boil down to this problem of density fitting, including generative modeling applications, where the goal is to find the best parametric map T theta, which maps a simple distribution, for example a Gaussian, to a more complicated distribution mu hat n by minimizing the distance between mu hat n and the transform distribution mu theta. In practice, T theta is defined through a neural network, which makes the evaluation of the density impossible, but one can still generate easily samples from mu theta, and in that case, density fitting is performed with a more adaptive framework called minimum expected distance estimation. So here, instead of considering mu theta, we generate samples from it. This gives us a second empirical distribution, mu hat theta m, and we minimize the empirical distribution between we minimize the distance between two empirical distributions. So this has nice computational properties, as the expectation can be estimated with a Monte Carlo scheme, and the quality of density fitting highly depends on the choice of the distance. So very recently, metrics emerging from optimal transport have been used. So very briefly, optimal transport is a way of comparing probability distributions by finding a way to move from one measure to another with minimal effort. And the standard metric emerging from optimal transport is called the Wasserstein distance. Estimators obtained by minimizing the Wasserstein distance have already made an impact in implicit generative modeling, since they form the basis of Wasserstein GANs and Wasserstein autoencoders, and because of this empirical success, the theoretical properties of such estimators have recently been taken under investigation. However, computing the Wasserstein distance is expensive, and the computational complexity of such estimators have become rapidly excessive with the increasing problem dimension. For that reason, there have been several attempts to consider more practical alternatives to the Wasserstein distance, for example, the slice Wasserstein distance. So when we compare it to one-dimensional distribution, the Wasserstein distance becomes easy to compute since it has a closed form solution, and this is what motivates the slice Wasserstein distance. So how does it work? Basically, we consider two distributions mu and nu that we want to compare, and we randomly pick a direction u, and we use it to project our two distributions along this direction. So we go back to the one-dimensional setting, and we can compute easily the Wasserstein distance since it has a closed form formula between two one-dimensional distributions. So we repeat this procedure for all possible values of directions, and the slice Wasserstein distance is the expected value of the Wasserstein distances computed between these projected distributions. So in practice, it has better computational efficiency than the Wasserstein distance, since it consists in solving several optimal transport problems in one dimension, and the integral is approximated with a Monte Carlo approximation, for example. So back to the minimum distance estimation problem, the estimators obtained by minimizing the slice Wasserstein distance have been empirically successful. For example, there is this slice Wasserstein GAN algorithm. However, the theoretical properties of such estimators have not yet been fully established. And in our study, we investigated the theoretical guarantees of such estimators in the regime. So our contributions are listed here, and they include first topological results saying that the convergence of measures under the slice Wasserstein distance implies the weak convergence of probability measures. We also proved the existence and consistency of the two estimators. And finally, we have a central limit theorem for this estimator So we characterize the asymptotic distribution as well as the convergence rate. And we prove that the convergence rate doesn't depend on the problem dimension, as opposed to the Wasserstein distance, where the convergence rate grows exponentially, gets exponentially slower with the problem dimension. Thank you for your attention. Please come by our poster. I will be happy to answer your questions and discuss.
Hello, everyone. I'm Joe. This talk is about theoretical analysis of adversarial learning. Our paper proposes theoretical methods for analyzing the generalization performance in the presence of adversaries. Our method is general in the sense that the adversary we consider is general and encompasses all LQ-bounded adversaries. And it can be applied to multi-class problems and commonly used loss functions such as hinge loss and rump loss. Before I go into our methods, let me first briefly recap the definition of IPMs risk. This is the standard definition of IPMs risk. I think everyone has seen it before. This is how we normally evaluate the quality of a classifier in machine learning. It takes average on the data points from the distribution P and then compute the loss of the classifier H on these data points. In reality, we usually want to find a classifier with a small IPMs risk. However, it's important to realize that this definition is compatible with classifier being very vulnerable to adversary attacks. In the presence of adversaries, what we are really care about is this definition, the adversarial IPMs risk. We still have equation here, but now, before feeding the data points to the classifier H, the adversary will first act on the data points. In our paper, we assume that the adversary will adversarially choose an example from the neighborhood NX, where NX can be any non-empty set, and give it to the classifier H for computing the loss. One important question is how the two notions of IPMs risk relate to each other. In particular, if the adversaries contain only zero vectors, then the adversarial IPMs risk will reduce to the standard IPMs risk. The main theoretical challenge here is to deal with the inner maximization problem. The trick we use in our paper is to introduce a transport map TH and push forward the original distribution P to a new distribution P prime, such that the adversarial IPMs risk under the original distribution P is equivalent to the standard IPMs risk under the new distribution P prime. This new distribution P prime is not fixed and depends on the hypothesis H. But we can prove that all these new distributions located within our Wasserstein ball centered at the original distribution P. By considering the local worst case risk, we can unbound the adversarial IPMs risk. To derive the adversarial response, we need to make some assumptions. We assume that the functions in the hypothesis space satisfy this pointwise Lipschitz condition. Here is our main theorem. Under the assumption with high probability, the adversarial IPMs risk is unbounded in this way, where this epsilon b is the radius of the adversary, and this lambda depends on the hypothesis f and the training set. It's the smallest value of lambda, satisfying this equality here. We are interested in how the adversarial response differs from the case when the adversary is absent. By setting the epsilon b to 0, the two terms highlighted in red here will disappear, recovering the Euler generation bound in learning theory. Therefore, the effect of adversaries is to introduce additional contribution to the empirical risk and an extra complicating term. We illustrate the application of our methods to commonly used models, SVMs, and deep neural networks. Here is a quick result. A key remark here is that our bounds has two data-dependent terms which can be optimized for achieving adversarial robustness. For more details, we'll come to our per section. Thank you for your attention.
Hello to everyone. My name is Gonzalo Mena, and I'm going to tell you about my recent work with Jonathan Naismith on the statistical aspects of entropic optimal transport. So it is a fundamental question for modern statistics and machine learning. How do we measure the distance between two distributions based on possibly high-dimensional and large sample datasets? Optimal transport, or OT for short, provides us with a sensible and robust way for comparing distributions that is based on sound mathematical and geometrical notions. Because of its flexibility and its efficiency, it has become very ubiquitous among the machine learning community. In this work, we address the following meta question. Why is the case that a certain variation of OT that we call entropic OT seems to provide very good results in practice? So first, to the left here, we have the usual OT cost, which is defined through an optimization problem, the one of the minimum expectation of the square Euclidean distance among all couplings between P and Q. And to the right, we have entropic OT, which is defined similarly, but instead now we are also adding a penalization, which is the mutual entropy of the coupling. So much of the success of the entropic OT has to do with computational reasons. 6 years ago, Marco Couturi wrote a paper in which he showed that entropic OT leads to an approximate solution of the original OT problem, but much faster. And there is a theoretical understanding of this, because like the original OT problem has a cubic complexity, while the entropic OT problem enjoys the much better quadratic complexity at the expense of the bias induced by the regularization. Here we are addressing the analog statistical question. So it is known that the OT is cursed by dimensionality. That means that we need an exponentially large number of samples in the dimension if we want to converge to the true cost. But we are wondering, like, do we also getting benefits in the case of entropic OT in terms of the sample complexity? This problem was recently addressed in recent breakthrough work by Doge DSGNbzuS1s6x81ZSbSHHV5uGDxJXePeyKy and colleagues. They showed that if the measures are defined in a bounded domain with diameter d, then the parametric 1 over square root of n rate is achieved with a bound that depends on the dimension and the diameter of the domain. We wanted to improve these results. So first of all, like, we noticed that there is an exponential blow up in this bound in the diameter. And moreover, like, we believe that the constraint that the domain has to be bounded might be too restrictive. So actually, like, we solve these two problems. And first of all, we get completely rid of the exponential term in the bound. And moreover, we extend the result for the much more general case of sub-Gaussian measures. And now the bound is going to be expressed in terms of the dimension and the sub-Gaussianity constant. In addition to this sample complexity result, we were able to prove a finer convergence result in the form of a distributional limit. This limit takes the form of a CLT for the empirical entropic OT, where the limiting variance expresses in terms of the so-called optimal dual potentials. So here in the figure, I'm showing the convergence of the empirical entropic OT to the true value, along with empirical confidence bands and the ones predicted by the CLT. And we see that for large n, they are in close agreement. Finally, we applied our results to the problem of entropy estimation. It is known that estimating the entropy of a large dimensional distribution is hard, but recent work has shown that if the distributions are corrupted by Gaussian noise, then the problem becomes much easier. And we developed a new estimator for this problem based on entropic OT that also achieves the optimal rate, and in this way we are providing a new perspective for this problem. So how this estimator works, we first establish a relation between differential entropy and entropic OT, and based on this relation then we can define a plug-in estimator based on entropic OT, And based on our previous results as well, we immediately obtained bounds for the estimation error as well as the distributional limit. We observed that in practice our estimator performed better than the best available before. Yeah, so that is our results. So if you want to hear more, you are all invited to see our poster session tonight. Thank you.
So hello everyone, I'm delighted to be here to present some research results in our team at Google with Olivier Teboul and Jean-Philippe Vert. I'm also very happy to give this short presentation after Gonzalo and Kimia's presentations because they're a bit related. So the title of the work is Differentiable Ranking and Sorting Using Optimal Transport. So the starting point of my presentation will be something you're all familiar with. So imagine you have an array of numbers, here let's say 5 of them, and you want to sort them. So you just give them to a computer that finds out that here the third element was the first, the fourth element was the second, etc. And what this is usually presented as mathematically is that the sorting permutation of that vector here was 3, 4, 2, 1, 5. In machine learning, and in a lot of algorithms in machine learning, we rely a lot on ranking and sorting. And in particular, rather than the sorting permutation itself, we usually use two byproducts of this permutation. And the first one is the ranks, the vector of ranks. So you would just give your computer an array and you would get an output which is an integer valued set of values, which here describes, for instance, that x1 is the fourth value relative to the others, x2 is the third, etc. And that's just the inverse sorting permutation. And the other one is the vector of sorted values, and that's the usual output of a sort call. So if you think about it, those two functions, ranks and sorts, are really important, but they are very brittle in the sense that they don't really carry out a lot of interesting differentiable properties. And to convince you of this, you can just look at this slide and imagine that you've changed a little bit the value of x4, you perturb it a little bit, and it's very easy to see that the vector of ranks itself has not changed at all. And the vector of sorted values is a bit degenerate in the sense that only, of course, the second value of the output would change. And this, you can picture this problem as saying basically that the ranking function is integer valued. It's valued in the space of permutations, and it's piecewise constant, whereas the vector of sorted values is basically a set of broken lines. So on the right-hand side, the sort is differentiable not almost everywhere, but sometimes we have lines, broken lines, and the other one, the ranks on the left, is really pathological. And so what we're trying to do here in this work is to provide a framework to give approximation functions for both rank and sort maps. And what we want is that those approximations are basically smooth. We can have a knob to adjust how much smoothness we want. You can easily parallelize them, and they are differentiable everywhere. And the way we get there is using optimal transport. So if you're not familiar with this theory, so we had two spotlights about it. Let me just give you an intuitive formulation. So imagine you are in a country and you have a resource that you have some mines extracting from the ground. And you also have factories that need those resources. And what the optimal transport problem is concerned with is to guess basically what would be the optimal way to move to ship around those resources. And so that means answering the question for each mine, where should it send its production? Or for each factory, where should it get its resources from? And the optimal transport problem basically solves that. And what you need to add a bit there is a conservation of mass principle and a way to compute the cost of moving the resource around. But that's basically what the theory has been doing for a few years, and a lot more things, of course. What is interesting is that there is a connection between sorting and optimal transport, where that is well known, and that was mentioned in Kimia's talk on sliced Wasserstein distances, which is that when your country actually is a line, so imagine you have a railroad, or Chile maybe, because Gonzalo is there as well, I'm happy to reference Chile. So you have this line, so you have factories and mines. And then in that case, it's known that the optimal transport is basically just moving monotonically from the left to the right. So what you would simply need to do to be optimal here is look at the leftmost mine, and send its production to a leftmost factory. And until you saturate those constraints, you keep on moving like this from left to right. So this is well known, as I was saying, and it's an established fact that basically ranking and sorting can help you solve the optimal transport problem. What we show in this paper, and it's a bit of an unusual route, and it's a bit like hitting a fly with a hammer. We say, no, actually, we're going to stick to optimal transport and solve optimal transport, and solve ranking and sorting using optimal transport. And this sounds like a stupid idea, but what we do is basically that we use the regularization that Gonzalo mentioned earlier to have access to differentiable algorithm. So in the poster, what you will see is a lot of numerics, some of the fine details of how to get this done, applications, and let me also mention that we have implementations available. So the poster number is 60, and I hope to see you there tonight. Thank you.
So the next oral actually is the outstanding paper, honorable mention awardee paper, non-parametric density estimation, convergence rates for GANs under Besov IPM losses. So if we could ask Ananya Upal, Shashank Singh, and Barnabas Pozos to the stage to accept their reward.
Hi, so thank you all for coming to the talk. I'm going to talk about joint work with Ananya Upal and Barnabas Pozos. This was done while we were all at Carnegie Mellon University. I'll be talking about new work in non-parametric density estimation that allows us to prove convergence rates and optimality guarantees for generative adversarial networks. So what we originally set out to do in this paper was to prove guarantees for GANs. Why would we want to do this? Well, GANs are notoriously hard to evaluate quantitatively, and they seem to solve problems that a lot of classical techniques can't solve. So we'd like to understand quantitatively why GANs are able to do so well. To analyze GANs, we're going to use machinery from non-parametric density estimation. And in particular, we're going to need to extend some of that machinery in a way that's going to not only lead to new insights about GANs, but also new insights about non-parametric density estimation itself. So more specifically, we're going to study a new generalization of density estimation. We're going to look at a new family of loss functions called Besov IPMs that are motivated by the discriminator functions in GANs. Under these new loss functions, we're going to prove new minimax convergence rates for density estimation. And I'll note that these rates, compared to a lot of classical rates for non-parametric density estimation, have much more benign dependencies on the dimension of the problem. So this might hint partly at why GANs are performing well. So we also show that compared to these minimax optimal rates, a lot of classical estimators, for example, kernel density estimators, are provably suboptimal. They can't possibly converge at the optimal rate. And moreover, the gap between the performance of these suboptimal estimators and the minimax optimal rates increases significantly with the dimension. On the other hand, certain constructions of GANs are able to achieve minimax optimal convergence rates. And finally, although we originally set out to prove results for GANs, as I said, Besov IPMs, we show, have an important role in the theory of nonparametric statistics, and so we're able to actually use these results to extend and unify many previous results in nonparametric statistics. In the interest of time, I'm going to focus on two of these contributions in particular. So I'm going to talk about this new generalization of density estimation and the optimality guarantees that we're able to make for GANs. So just to set the stage, most of you are probably familiar with density estimation, but what we're doing is we have n IID samples from a probability distribution P. we assume that P lies in some kind of nice class of distributions. Let's call it script P. And our task is to estimate the distribution P. So visually what this might look like is we have a density shown in blue. We observe samples shown in red. And then we can use, for example, a kernel density estimator to construct this estimate shown in black of the blue density. So it's well known that kernel density estimators and most other nonparametric estimators perform very poorly in high dimensions. And one tool that the machine learning community has adopted to perform tasks that are very similar to density estimation in high dimensions are generative adversarial networks, GANs. So most of you probably know that GANs train two neural networks, a generator which tries to generate new data, and a discriminator which tries to distinguish this generated data from the original training data. And these work nicely in practice because you can plug these networks together and then you can apply standard neural network tools like backprop. To prove theoretical guarantees for GANs, we're going to need to write them down in mathematical notation. So what does that look like? I've written this equation at the bottom of the slide. We have a discriminator which has a class script f of functions that its neural network parameterizes. And we have a generator which has a class script p of functions of distributions that its neural network parameterizes. And for a given generator distribution q, the discriminator is trying to find the function f whose expectation maximally distinguishes the generated distribution q and the empirical distribution pn. So here I've copied the same equation from the previous slide. And I'm going to rewrite it a little bit so that you might see that it fits a more conventional learning theoretic form. In particular, let's group the second part of the expression, and let's call it df. If you look at this, you might recognize this as empirical risk minimization, where we're trying to minimize a loss df over some class of hypotheses, script p. And I'm going to say regularized here because we may not actually want to use the original training data, PN. In particular, in our analysis, we're going to assume that we regularize the data before feeding it to the GAN. What we do in general is a little bit complicated, but in many cases, it reduces to this trick called instance noise that was introduced a few years ago and is fairly commonly used in training GANs. So these losses that I wrote df, they have a name. They're called integral probability metrics, or IPMs. IPMs are parameterized by a function class script f, and they're defined by this particular equation here. So just to reiterate, for a given distribution p and another distribution q, the IPM distance between p and q is the maximum overall functions f in this script f class of the difference in expectations between p and q. So to visualize what that looks like, I've given two examples here. So in both figures, I have two distributions, one in orange and one in blue, and also a discriminator function in green. So on the left-hand side, the discriminator function is restricted to be Lipschitz, and this gives rise to the Wasserstein metric that we've heard a lot about in this session. And this is used, for example, in Wasserstein GANs. On the right-hand side, I've constrained the discriminator function to lie in a reproducing kernel Hilbert space. So it's a lot smoother, as you can see. And this is used, for example, in MMD GANs. This metric's called maximum mean discrepancy, or MMD. So I've mentioned already that Wasserstein distance and MMD are examples of IPMs. It turns out that almost every metric that's used commonly in between probability distributions can be expressed as an IPM. So this is a very general class of metrics. In particular, all of the results that we prove are going to apply to the metrics that are listed here, many of which I assume you're familiar with. So how do we achieve this kind of generality? We're going to use a family of function spaces called Bestofspaces. Bestofspaces are specified by two parameters, S and P. And the very general definition of a Bestofspace is very complicated to express. For the purpose of this talk, let's consider the case where S is an integer. In this case, you can roughly think of the Bestofspace BSP as the class of functions f in LP that are S times differentiable and whose S derivative is also bounded in LP. So for And familiar examples might be the Lipschitz and Holder spaces, which correspond to p equals infinity, or sublove spaces corresponding to p equals 2. So I've been talking about abstract function spaces. What does this have to do with neural networks? Let's go back to that ERM estimate I mentioned earlier. If script p and script f are these infinite dimensional function classes, how can we actually compute this estimator? So there's recent work showing that these Bestofspaces can actually be approximated well by fully connected neural networks with ReLU activations. And there's a precise theorem that depends on where you show that for a network of a given, say, depth and width and number of weights, you can approximate Besof functions to a particular specificity. The important thing for us is that this means we can effectively plug in neural network classes for these script p and script f. So this thing I've written at the bottom of the slide is exactly what a GAN does. It optimizes over these neural network classes. And basically the main theorem of the paper is that GANs are optimal in a certain sense. So this GAN that I've written is optimal for estimating distributions that lie in a Besov space under Besov IPM losses. Of course, that optimality comes with some caveats. So the biggest one is that we assume that, again, that you can compute this minimization perfectly in this case. And that, of course, may be computationally challenging. There's been a lot of work on trying to actually compute the optimum for GANs, but this is still a challenging open problem. Second, we assume that these neural networks are tuned, by which I mean that the size is appropriate for A, the sample size that you have, and B, the size of the Besov spaces that you're trying to approximate. So this is sort of related to our neural architecture search, and again, this is a hard open problem. And finally, this work is restricted to fully connected ReLU neural networks. It would be nice to try and adapt to convolutions or other kinds of layers that are used in neural networks. So just to wrap up, these are the results we had. I focused on 2 of them here, but please come to the poster tonight to talk in detail about the other results, and I'll be happy to take any questions.
So do we have questions? Come up to the mics. Okay, can you say maybe the punchline of one of the other bullets that you didn't get to?
Yeah, so I guess, so there's new rates, as I said. So one thing is that these rates are deal much better with large dimensions. So in certain cases, you get parametric convergence rates even in high dimensions. The rates are much better than what you're used to seeing for non-parametric density estimation. That's probably one of the big points. Otherwise, in terms of results for non-parametric statistics itself, as I said, we have this big class of loss functions that we're able to get minimax rates for. Earlier, people have been proving results for each of these loss functions separately, and we're able to wrap them all into a single result. So those are some of the other contributions.
Nice. Okay, let's thank the speaker again and transition into Spotlight.
This is not my presentation, sorry. All right. You want? Okay.
Hello everyone. I'm Jen. I will talk about the kernelized graph matching. Firstly, I will introduce the concept of graph matching. Graph matching problem aims at finding the optimal correspondence between the nodes. It has applications in image registration, pattern recognition, and protein-protein interaction network alignment. In the red figure, I show an example of landmarks matching in computer vision. And we want to find the correspondence between the landmarks. And the correspondence can be further be applied in video tracking and object segmentation. graph matching problem can be formulated as two types of quadratic segment problems: the Kuhlmann-Beckmann QAP and the Lawler's QAP. For the Kuhlmann-Beckmann QAP, we want to find the permutation matrix to maximize the node attribute similarity and to align the adjacency matrix. For the Lawler's QAP, we want to find a permutation matrix to maximize both the node similarity and edge similarity. And both of them has advantage and disadvantages. For the Kuhlmann-Beckmann QAP, it has well-designed the convex and concave relaxations, and it has low space complexity. But the problem is that it cannot encode the edge similarity. For the Lawler's QAP, it will encode both the node and edge attributes. However, it is not easy to get the convex and concave relaxations, and it has extremely high space complexity. In practice, if we want to solve the Lawler's QAP with 1,000 of nodes, we need to pre-compute a huge matrix of the size of 1 million multiplied by 1 million. That is impractical. It is impossible in practice. So in our work, we provide a unifying view for Kuhlmann-Beckmann and Lawler's QAP. It is based on a very mild assumption that the edge affinities are characterized by kernels. So we can rewrite the Lawler's QAP as the Kuhlmann-Beckmann alignment between two arrays in Hilbert space. It allows us to solve the Lawler's problem without pre-computing the huge matrix. We also develop the convex and concave relaxations and numerical algorithm to optimize QAP. And notably, in practice, we can solve the Lawler's graph matching problem with thousands of nodes in about 10 minutes. And our work is based on the assumption that the edge affinity function is a kernel. So based on that assumption, the graph can be represented by a Hilbert array. And if we properly define the multiplications between a Hilbert array and a matrix, we can rewrite the Lawler's QAP in the following form. And we want to find a permutation matrix to maximize the node similarity and to align the Hilbert arrays. And the following is the Kuhlmann-Beckmann QAP. We can see that the Lawler's QAP can be written as the exact form of the Kuhlmann-Beckmann QAP. And based on the rewriting form, we can develop the convex and concave relaxations by the following strategy. We also develop the numerical optimization method to optimize that. And here we briefly show some experiments, and we can see that our method has the good performance in both the matching accuracy and the computational time. And this is the graph matching results on the protein-protein network alignment. Thanks for your attention. If you have interest in our work, please come to the poster 145. Thank you.
All right. Sorry for spoilers early on. So my name is Matteo Togninalli, and I'm a PhD student at ETH in Zurich. And I'm extremely pleased to present our work on Wasserstein-Weisfeld-Lehmann graph kernels. This is a shared effort with Elisabetta, Bastian, Felipe, and our advisor, Karsten Borgward. As many of you know, probably know, graph structured data are ubiquitous, with applications spanning from bioinformatics to traffic modeling, passing by social networks. In order to come up with efficient machine learning algorithms that work well with graphs, we have, however, to also devise good and reliable similarity measures between these graphs. And this is what has been done in the community for several years now, and it's especially important for a graph classification task, where one wishes to classify graphs based on their topology and features. So several graph kernels have been proposed over the last years, and most of them rely on the so-called R-convolution framework. So for which one wishes to decompose a structured object into substructures, compute similarity measures between these substructures, and then aggregate the similarity measures to obtain a kernel value between the two structured objects. In the case of graphs, the same thing can be done, and one can see a graph as a set of nodes, of edges or paths, and compute the kernel values, base kernel values between these substructures, then aggregate these joint kernels to obtain a similarity measure of the graph. However, most graph kernels nowadays rely on simple way to aggregate these similarity measures. And this is also the case of the Weisfeier-Lehmann kernel that simply takes the average of the linear kernels between the substructures. Now, in order to avoid this pitfall, we too rely on dividing graphs into substructures in sets of nodes, to be more precise, and we come up with node embeddings that can capture both the topology and the features of the graphs. But instead of considering these as pure sets, we consider them as empirical distributions. And we therefore apply optimal transport derived metrics, such as the Wasserstein metric, on to these distributions. From this distance, we then apply a Laplacian kernel to obtain a similarity measure between the graphs, having therefore a more subtle way of distinguishing between graphs. In practice, we show that this beats the state of the art for both continuously attributed graphs and categorically labeled graphs. However, what's particularly important in this slide is that our method in blue always and constantly outperforms the baseline of a naively applied R-convolution kernel framework in green. For this particular example, we took the exact same embedding scheme, and instead of applying Wasserstein distance on the embeddings, we computed the RBF kernels of each pair of nodes for the two graphs, and then averaged these kernel values to obtain the object-level kernels. So this is to show that the fact of considering graphs as empirical distributions of nodes and not only as sets of nodes clearly has an edge and can benefit in classification performance. This brings me to the conclusions. So we present a novel similarity measure between graphs that can be used to accurately classify both categorically labeled graphs and continuously attributed and weighted graphs. And we're very excited about future potential directions of this, and notably in GCNs. If you're interested in discussing these, please come and see us today at poster number 12, or contact us directly via email, since the poster sessions are a bit crowded. Thank you very much, and I wish you a great end of the conference.
Hi everyone, I'm Colin Wei, and I'm going to talk about comparing neural networks versus the NTK, their induced kernel method, and this is joint work with Jason Lee at Princeton, Qiang-Yu at UT Austin, and Tongyi Ma at Stanford. So the NeuroTangent Kernel, or the NTK, is a recent attempt to explain the successes of deep learning. However, our work tries to shed light on whether it's actually a valid way to do so. Basically, the NTK says that if you have a specific learning rate and initialization scale, then gradient descent will learn a kernel method using the features obtained via a random initialization. However, there are several reasons why it can't explain generalization. So first of all, the learning rate and initialization scale that you use is unrealistic, so it doesn't mirror what happens in practice. And in practice, neural networks actually outperform kernel methods. And then finally, the NTK doesn't allow for L2 regularization. So it breaks down if you add an L2 regularizer. So in our work, we try to look at this last bullet point. What can we say about optimization and generalization when an L2 regularization is involved? So the first main result that we show is that if we have an L2 regularizer, the neural network can generalize much better than the NTK. So in our work, we show that there's a distribution in d dimensions for which the NTK requires omega of d squared samples to learn, but the L2 regularized logistic loss on a neural network requires only O of d samples. And the way we construct this distribution is pretty simple. So we'll have the first two coordinates. For the first two coordinates, the label will be plus or minus 1 with probability 1/2. And if the label is +1, then there's a component along the first dimension. And if the label is -1, then there's a component along the second dimension, as visualized in the figure on the right. And the remaining d-2 coordinates will just be noise. So what will happen is that the NTK will overfit to the noise in the distribution, whereas the regularization will allow the neural network to focus on the signal in the first 2 coordinates. And so it will only focus on those first 2 coordinates and not overfit to the noise. And so the takeaway here is basically that if we add an L2 regularizer, it can allow the network to adaptively choose which features in the data are important, whereas the NTK can't do so. So the second main result on the statistical side is that if you have the global minimizer of a regularized logistic loss, then you approximately get a max margin neural network. So this is used to prove the sample complexity gap, but it's also a result of independent interest. So if we consider the following training objective, which is the logistic loss plus some regularization on the norm of the parameters, then we show that if the network is homogeneous, the global minimizer will approach a max margin solution as the regularization strength approaches 0. And this result will hold regardless of the depth of the network. So for example, it will hold for any feed-forward ReLU network as long as it's homogeneous. And then if we combine this with generalization bound of Golowich in 2017, Golowich et al. In 2017, we can say that the generalization of this global minimizer is bounded by the inverse maximum possible margin. And since this maximum possible margin is non-decreasing with the width of the network, this implies that increasing the size of the network improves the bound. So this at least gives one explanation for why if you have a network with more capacity, your generalization can improve. And finally, the last thing we look at is optimization. So in the previous slides, we said that you get good statistical properties if you minimize this regularized logistic loss. But there's still the open question of how do we obtain a global optimizer of the loss. So at least for infinite width 2-layer neural networks, we can show that noisy gradient descent will converge to a global optimizer in a polynomial number of iterations. So to conclude, so first we examine the statistical properties of a neural network if you have an L2 regularizer. And we can show that it can generalize much better than the NTK. And we also show that the global minimizer of this regularized loss will approximately become a max margin solution. And for the optimization side, we show that if you have an infinite width 2-layer net, the noisy gradient descent will find a global optimizer in a polynomial number of iterations. And for future work, there's a question of optimization for a finite width neural network that's regularized. And if you're interested in finding more or learning more, come find our poster number 236. Thank you.
So today I will present the work that has been done with Yael Varocco on improving kernel two-sample testing thanks to the L1 geometry. So assume we are given two samples, x and y, from two unknown distributions, p and q. And for example, you can think of the distribution of the location of the restaurants McDonald's and KFC across the United States. And the problem that you want to solve is to know if the two samples are drawn from the same distribution. So to answer the question, we decide to design a two-sample test where the goal is to determine whether the difference between the population is statistically significant. And therefore, our new hypothesis will be to know if the distribution are the same. So what is the test that we have designed? From the two samples x and y, we are given a kernel, in that case a Gaussian kernel, and you can in fact embed the samples in a Hilbert space, which is a reproducing kernel Hilbert space associated to the kernel. And now, instead of having samples, you obtain a function to represent the distribution. And from these functions, which are called the min embeddings, you can compute the absolute difference of these min embeddings and obtain a witness of the difference between the two distributions. And then you can sample on the sample space J location and compute the absolute difference between the mean embeddings as the J locations and obtain a vector. And now, from this vector, you just have to compute the LP norm to the P times n to the P over 2, which gives us the statistics that we have studied. In fact, these statistics come from a metric which has the nice property to metrize a weak convergence. So what does it mean? It means that for a sequence of distribution, alpha n, this sequence will converge toward a target distribution alpha if only if the distance goes to 0 as n goes to infinity. So to illustrate this, you can think about a sequence of Dirac, which converge weakly to a target Dirac. And if your metric does not metrize a weak convergence, the distance according to this metric can be huge even if those Diracs are very close. But if your metric metrizes weak convergence, then the distance will go to 0 as n goes to infinity. So, for example, our metric goes to 0 and the total variation is constantly equals to 2. So how to perform the test? You just have to compute the statistics and reject the null hypothesis as soon as the statistic is bigger than a threshold, which is just the 1 minus alpha quantile of the asymptotic null distribution. In fact, when p equals 1, under the alternative hypothesis, which is when the distributions are not the same, with high probabilities, the L1-based statistics will reject better the null hypothesis. So to conclude, you observe that under the alternative hypothesis, when using analytic kernels, you obtain mean embeddings which are analytics functions, and therefore the difference will be dense. This difference is better captured by the L1 geometry. Also, we have considered statistics based on other representative of the samples, which are the smooth characteristics functions, and obtain similar results. Finally, we have normalized our statistics to obtain a simple null asymptotic distribution to compute the quantile, and we also learned the location where the distribution differs the most. Thank you very much.